Hello friends and my dear students, I welcome you all to my channel. This video is part of the playlist NCERT Mathematics of class 10. In this playlist, I will continuously upload videos on the discussion of the chapters sequentially. I will try to follow the NCERT textbook thoroughly as much as I can, and will take notes of the important concepts. We'll walk through the solved examples, and also we'll try to solve the problems in the in the exercise. So if you are following my videos, then I will highly recommend that you uh, sit down with a notebook and a pen and study the chapter with me. Uh, Take notes of the important concepts, and also uh, also take notes of the formulas that are required to solve the exercise problems. Uh, Before I start, I will highly appreciate and request you to support me by subscribing to my channel. Like my videos if my videos are helping you in learning mathematics. In whichever class you are, I make videos from class 6 to 12 on mathematics, and share my videos with your friends and subscribe to my channel, and do not forget to press the bell icon so that you will be notified by my videos which I will upload in the future. In this video, I'm starting the chapter 1 of Mathematics 10 of NCERT book, that is the real numbers. This is lecture number 1. In this lecture, I will cover uh, the introduction part, the Euclid's division lemma, the fundamental theorem of arithmetic, and how to compute HCF and LCM of two positive integers using the fundamental theorem of arithmetic and Euclid's division lemma. Also, I will try to solve all the problems of exercise 1.1. So let's get started with this video. Okay, let's start. I have the PDF version of the NCERT textbook open on the left hand side, and on the right hand side in the notepad I will take notes and will explain things as and when necessary. So you can follow along with me and study this chapter with me. I hope I will be able to uh, uh, make a good understanding of this chapter with the best of my ability. So let's get started. Okay. So in the introduction, it says that in class 9, you began your exploration of the world of real numbers and encountered irrational numbers. So in 9, the first chapter was, I guess, uh, number systems, where you learn about the irrational numbers like root 2, root 3, that is numbers which cannot be written in the form of p by q, where p and q are integers and q not equals to 0. You learned how to represent irrational numbers and rational numbers on the real number line. Now, in this chapter, you will the two important things that we will learn is Euclid's division algorithm. We will learn Euclid's division algorithm, and the fundamental theorem of arithmetic. Okay, what does Euclid's division algorithm says? It says that it has to do with divisibility of integers. The main purpose of this algorithm is about divisibility of integers. Now, what is the algorithm says? That the algorithm says any positive integer a can be divided by another positive integer b in such a way that it leaves a remainder r that is smaller than b. So, uh, uh, any positive integer a can be divided by another positive integer b such that uh, in such a way in such a way that it leaves a remainder r where r is less than b. So this process, when you divide an integer a by another integer, positive integer b, you have done this division in your previous classes using the long division method, where you have seen that either you will be left with a remainder, there will be some remainder, or there will be no remainder, that is zero remainder. So and basically it says that a is equals to this, where we are dividing a positive integer a by another positive integer b, and we are getting a quotient q, and the division process leaves the remainder r, where actually r should be less than equal uh, where r is actually greater than equal to 0, less than b. It is it is definitely less than b, but it can also be 0. If b perfectly divides a, then we will have no remainder. That is 0 zero remainder when you do long division method using uh, just like if you divide 4 with 2, you have no remainder. In that case, r is 0 and quotient is 2. When you divide 15 by 3, the quotient q is 5 and the remainder is 0. But when you divide, let's say 7 by 3, 7 by 3, you get the remainder 1 and a quotient 2. So this is basically the Euclid's Euclid's division algorithm. It says that this algorithm has many applications in mathematics, one of being the divisibility properties of integer. So the this divisibility of integers is an application of the Euclid's division algorithm. Another application of Euclid's division algorithm is, okay, so uh, we can say applications are one, divisibility divisibility properties of integers, and number two, another application is to compute the HCF of two positive integers. So it has two applications. Euclid's division algorithm has two applications. One is regarding divisibility properties of integers. Another one is to compute the HCF, which is highest common factor of two positive integers. Okay, let's proceed with the textbook. Now, the fundamental theorem of arithmetic. What does the fundamental theorem of arithmetic says? Fundamental theorem uh, of fundamental theorem of arithmetic. How is fundamental theorem of arithmetic applied in mathematics? It says, on the other hand, has to do something with multiplication of positive integers. Multiplication of positive the fundamental theorem of arithmetic is all about multiplication of positive integers. It says that you already know that every composite number can be expressed as a product of primes in a unique way. This important fact is the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic says that any composite number, by composite number means the numbers which are not prime are the composite numbers. And what are prime numbers? A number which has no factor other than the number itself and 1, like 2, 3, 5, 7, 11, 13, 17, 19. These are prime numbers. And what are composite numbers? Composite numbers means it has at least two factors uh, other than the number itself and 1, like 4. It has two factors, 2 into 2, like 6, 2 into 3, like 10, 2 into 5. All these are composite numbers. And it says that every composite number can be expressed as a factor of prime numbers. This fact is known as the fundamental theorem of arithmetic. Now it says that while it is a result that is easy to state and understand, it has some very deep and significant applications in the field of mathematics. So we use the fundamental theorem of arithmetic for two main applications. First, we use it to prove the irrationality of many of the numbers you studied in class 9, such as root 2, root 3, root 5. So it says that this fundamental theorem of arithmetic is used to prove that root 2, root 3 and root 5 are irrational numbers. Secondly, it says the another application is we apply this theorem to explore when exactly the decimal expansion of a rational number, say p by q, is terminating and when it is non-terminating repeating. In class 9, you have already learned about the rational numbers which have terminating decimal and rational numbers which have non-terminating and recurring or repeating decimals. So this fundamental theorem of arithmetic can be used to prove which rational number has terminating decimal and which rational number has non-terminating but and recurring decimal. So how does it how that is done? It says we look at the prime factorization of the denominator q of the rational number p by q. You will see that the prime factorization of q will completely reveal the nature of the decimal expansion of p by q. So it says that given a rational number p by q, if we since q is an integer, it can be expressed as a factor of prime numbers. So if we see that prime factorization of q, it will reveal whether a decimal expansion of the rational number p by q will be terminating or non-terminating recurring. So it says let us begin our exploration. Let's try to understand how do we do this. Okay, so fundamental theorem of arithmetic. Okay, so in your earlier classes, you have seen that any natural number can be expressed as a product of its prime factors. For instance, 2. Let me just point out the important facts. Any natural number can be written as a product of its prime factors. So any natural numbers that are indeed positive integers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, these any natural number can be written as a product of its prime factors. For example, for example, for example, we can say that 2 is a natural number. It can be expressed as 2 into 1. So it has factor 2. It has factor 2. We need not write the 1. So 2 is 2, and so the only factor of 2 is 2, which is a prime number. So what about 4? 4 is 2 into 2. It has two factors, and both the factors are 2, and 2 is a prime number. So it also says that 253, which is 11 into 23. 11 is a prime number and 23 is a prime number. Let's see 10. How can we factorize 10? 2 into 5. 5 is a prime number, 2 is a prime number. Let's say 16. How can we factorize 16? We know that 16 is 4 into 4. This can be written as 2 into 2 and 2 into 2. So we have 4 factors where each factor is 2. So, and these two, all the factors, 2 is a prime is a prime number. Just 3. 3 is a prime number, 5 is a prime number. Let's say 20. 5 into 4, which is 5 into 2 into 2. So the prime factors of 20 are 5 and 2. We have the factor 2 twice and 5 once. So in this way, any natural number can be written as a product of its prime factors. Now it says, now let us try and look at natural numbers from the other direction. That is, can any natural number be obtained by multiplying prime numbers? So it says that we know that a natural number, given a natural number, we can write it as a product of its prime factors. Now, the question it asks is, can we produce a natural number by taking factors of some, by multiplying some prime numbers? Can we it says that by multiplying some prime numbers, can we generate or can we create all natural numbers? That is the question. So it says, take any collection of prime numbers, say 2, 3, 7, 11 and 23. If you multiply some or all of these numbers, allowing them to repeat as many times as we wish, we can produce a large collection of positive integers, in fact infinitely many. Let us list a few. So it is trying to see whether using some prime numbers, here it has taken 2, 3, 7, 11, 23, these are prime numbers. Using these prime numbers, can it, what are the natural numbers it can generate? So first it has multiplied the point is, uh, can any natural number be obtained by by multiplying prime numbers. This is the question that is trying to address. So it has taken the prime numbers uh, it has taken, for an example, the collection of prime numbers 2, 3, 7, 11 and 23. These are all prime numbers, and it is trying to see, using these prime numbers, what all natural numbers it can generate by multiplying these prime numbers, and uh, uh, also it can uh, use one prime numbers more than once. So 11 into 7 into 11 into 23, we are getting 1771. Okay, so again 2 into 3 into 7 into 11 and into 23, we are getting 10626 and so on. So we have two other examples. So let's say let's try to create some natural numbers on our own. Let's say if we take twice the prime number twice, take factor 2 times the factor of 2. Let's say we do 3 and the 7. What do we get? 4 into 3 into 12 into 84. So and this way we can generate a lot of natural numbers by using these 5 prime numbers. This is the basic idea. Now what it says, now let us suppose your collection of primes includes all the possible primes. In this example, we were trying to obtain natural numbers by using only the collection of prime numbers, which are 2, 3, 7, 11, 23. But there are, as you know, infinite number of prime numbers. There are endless prime numbers. So it is now saying, what if we use the collection of all the prime numbers, and so it says, suppose your collection of primes includes all the possible primes. What is your guess about the size of this collection? Does it contain only a finite number of integers or infinitely many? In fact, there are infinitely many primes. So just as a point to be noted, there are infinite number of prime numbers. And so if we combine all these primes in all possible ways, we will get an infinite collection of numbers, all the primes and all possible products of primes. So since the collection of all prime numbers is infinite, if we if we consider all possible ways of multiplying the prime numbers, we will get lots of possible number of natural numbers. So if we combine all these primes in all possible ways, we will get an infinite collection of numbers. All the primes and all possible products of primes. The question is, can we produce all the composite number this way? So a good question is, uh, can we produce all composite numbers by uh, by uh, considering by considering entire collection of primes. Can we produce all composite numbers by considering entire collection of primes and all possible ways to all possible ways to multiply the primes. So we have the collection of infinite number of prime numbers, and by considering all the possible ways of multiplying some prime numbers, can we generate all the composite numbers? This is the question. What do you think? In the textbook it says, what do you think? Do you think that there may be a composite number which is not the product of powers of primes? So as you can see, we can we have already seen that any composite number can be factorized, can be written by can be written as a factor of primes, and in those factors of primes, one prime can be multiple times. So we will essentially have some powers of primes as a factors of a composite number. So the next question is a good question, that uh, can any composite number be expressed? It says, do you think that there may be a composite number which is not the product of powers of primes? Okay, so it is trying to understand, it has raised a question, it is trying to uh, ask, it is trying to verify this question, that is there any composite number that cannot be expressed as the product of powers of primes. So it is asking a question, that is there any composite number that cannot be factorized, that cannot be written as a factor of all primes, or possibly some powers of all some primes. So before it, in the textbook it says, before we answer this, let us factorize positive integers, that is, do the opposite of what we have done so far. Opposite of what we have done so far. We are going to use the factor tree with which you are all familiar. So this is a factor tree which you must have learned in your previous classes, that we can factorize a given positive number like this, and we get all the factors. So as an example, it has taken the number 32760. Let us take some large number, say 32760, and factorize it as shown. So as you can see in the textbook, it has factorized 32760 and has shown the factor tree. Now what does it say? So we have factorized 32760 as 2 into 2 into 2 into 2 into 3 into 3 into 5 into 7, 13 as a product of primes. So what it has done, uh, factor tree of large number 32760. Mm, it's a long tree. I won't write it down. Just I will write the factorization. So we can it has factorized 32760 as the factor of primes, which is 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. From the factor tree, as you can see here, we have the factors 2, 2, 2, 3, 3, 5, and 7. So we get 32760 can be written as a factor of all these numbers, and all these numbers on the right hand side are prime factors. So this is basically 2 is 3 times, so 2 to the power 3, 3 is factor 3 is 2 times 3 square, and then 5 into 7 into 7, then into 13. So we have factorized the large number 32760 as a factor of primes like this. Now let us try another number, which is a very big number, that is 1, 2, 3, 4, 5, 6, 7, 8, 7, 8, 9. This can be written as also as an example. If we factorize 1, 2, 3, 4, 5, 6, 7, 8, 9, it will be, if we factorize this, the prime factors will be 3 square into 3803 into 3607. Now it says, of course, you have to check that 3803 and 3607 are primes or not. We have factorized this big number as 9 into 3803 and 3607. Now we know that 3 square, 3 is a prime number, but we have to check whether 3803 is a prime number or not, and also 3607 is a prime number or not. Uh, of course, you have to check, try it out for several other natural numbers yourself. This leads us to a conjecture that every composite number can be written as a product of powers of primes. In fact, this statement is true and is called fundamental theorem of arithmetic because of its basic crucial importance to the study of integers. Let us now formally state this theorem. So far, we have not formally stated what is fundamental theorem of arithmetic. We were just jotting down the points and the concepts given so far from the textbook. Now let's formally write down the uh, theorem. That is, it says theorem 1.1, fundamental theorem of arithmetic. So what does it say? What is this? What does this fundamental theorem of arithmetic say? That every composite number can be expressed. Expressed means also factorized. Has the same meaning. Expressed means you are factorizing the composite number as uh, a product of primes, and these factorization is unique apart from the order in which uh, the prime factors occur. This is the formal statement of fundamental theorem of arithmetic. So what does it say? It says every composite number can be expressed or factorized as a product of some primes. And this factorization is unique, meaning uh, there doesn't exist any other factorization which will have some different primes as a factor. So it will have a unique product of primes, and uh, the order of the primes as a factor does not matter. So let's see if we can. So it says, I will skip the historic part. So it says the fundamental theorem of arithmetic says that every composite number can be factorized as a product of primes. And actually it says more. It says that given any composite number, it can be factorized as a product of prime numbers in a unique way. This is important. So prime factorization of a composite number is unique. You cannot have a factorization of a composite number cannot be factorized in two different ways. In one way you're having some prime numbers, and in another way, in other factorization you're having some other prime numbers. No, they will be same. You may The order of the prime factors may differ, but the all the prime factors and their powers will be same. That's what it means when it says that given any composite number, it can be factorized as a product of prime numbers in a unique way. Okay, so that is, given any any composite number, there is only one way to write it as a product of primes. This is important. Given any composite number, given any composite number, there is only one way to write it as a product of primes. Given a composite number, you can factorize it as a factor of primes in only one way. There is no two way. There is only one unique way. For example, it says that 2, 3, 5, 7, 6, 30 and 21. If we factorize the composite number 210, what it will be? What it will be? 2 into 3 into 5 into 7. No, 6, 30. Yes. Okay. Now, someone may factorize this 210 as 3 into 5 into 7 into 2. The second factorization still gives 210, but the second factorization is no different from the first factorization, because in both these two factorization we still have the same prime numbers as the factors, like we have 2, 3, 5 and 7, and the powers of all the prime factors are the same. That is, all the powers of all the prime factors are 1. So uh, it says this fact is also stated in the following form: the prime factorization of a natural number is unique except for the order of its factor. Okay, we should write it down. The prime factorization of a natural number is unique except for the order of its factors. By order of the factors means that in this example 210, in the first factorization the order was 2357, but in the second factorization the order was 3572. So order may be different, but the prime factors will be same and the powers will be same. That is what it is trying to say, that the prime factorization of a natural number is unique except for the order of its factors. I hope it's clear. Now let's move on. So now it gives a mathematical statement or mathematical formulation of the factorization of a composite number. So what it says that uh, in general, given a composite number x, we can factorize it as x equals to p1 into p2, likewise into pn. So it is uh, 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 for a composite number x, uh, we have its prime factorization as x equals p1 into p2 into p3, this way. So if the composite number x has the prime factors p1, p2, p3 up to pn, so if it has n prime factors which are p1, p2, p3, pn, where so where p1, p2, p3 up to pn are primes, uh, and written in ascending order and written in ascending order means in increasing order, which means that p2 is greater than p1, p3 is greater than p2, and like this in ascending order, that is p1 is less than equals to p2 is less than equals to p3, likewise less than equals to pn. If we combine the same primes, we will get powers of primes. So we have factorized a composite number x into its prime factors, and the prime factors are p1, p2, p3, pn, in such a way that if we write p1, p2, p3, up to Pn in such a way that P1, P2, P3, Pn are in ascending orders. That is, P1 is less than equals to P2, is less than equals to P3, is less than equals to P3, Pn. Now, in this P1, P2, P3 up to Pn, some prime numbers may occur more than once. So, if we combine the multiple occurrence of a prime number, we will have the powers of a prime number. So, it says that if we combine the same primes, we will get powers of uh, if we combine uh, the same primes, we get powers of primes. Now, as an example, it says that 3, 2, 7, 6, 0, if we factorize it as a prime factors, and if we write the prime factors in ascending order, what we get is 2 into 2 into 2 into 3 into 3 into 5 into 7 into 13. Now, if we combine the same prime numbers, we get powers of primes. So, if we combine the 2 prime number, we get 2 to the power 3 because we have 3 times 2. Similarly, if we combine the 3, we get 3 squared, and the rest remains the same. So, we get powers of primes, like the powers of 2 here is 3 and the power of 3 is 2. Once we have decided that the order will be ascending, then the way the number is factorized is unique. If we, so it says, so if we factorize the composite number x in such a way that the prime numbers, the prime factors are arranged in ascending order, like P1, P2, P3, Pn, where P1 less than equals to P2 less than equals to P3, and then if we combine the similar prime numbers, the final representation that we get over here, this is the final representation of the factorization of the number 32760, where all the primes are written in ascending order and the similar primes have been combined. Now, this representation is unique. For this number, if you factorize it, if you arrange all its prime factors in ascending order and combine all the similar primes and have powers, you will always end up with the same representation. This will be unique. So that is what it says. The fundamental theorem of arithmetic has many applications, both within mathematics and in other fields. Let us look at some examples. So now it is trying to have some example where we are applying the fundamental theorem of arithmetic to solve some problems. So example 1, it's what it says: consider the number 4 to the power n, where n is a natural number. Check whether there is any value of n for which 4 to the power n ends with the digit 0. It says the question is, check whether for any natural number n, the number 4 to the power n ends ends with the digit 0. So what is the problem? What is the question? The question is, we have, if we take a number 4 to the power n, where n is a natural number, it is asking, is there any natural number n such that the number 4 to the power n will have 0 as the last digit? So it says, the solution says, if the number 4 to the power n for any n were to end with the digit 0, then it would be divisible by 5. So definitely, if a number has a digit 0 as the last digit, it is definitely divisible by 5. That means, if such n exists, and if 4 to the power n indeed ends with the last digit as 0, then 5 should be a factor of 4 to the power n. That is, it says, that is, the prime factorization of 4 to the power n would contain the prime 5. This is not possible because 4 to the power n. Okay, so how does it solve? If it says, I'm writing the solution in a very short form. If 4 to the power n has to end with the digit 0, then it must be divisible by 5. This implies, it means that 5 must be a prime factor of 4 to the power n. Now, it says this is not possible. It says that prime 5 cannot be a prime factor of 4 to the power n, because now it says not possible. This is not possible because it is rewriting 4 to the power n as, we know 4 is 2 to the power 2 and we have 4 to the power n. Uh, so, uh, okay, so it says that we can write 4 to the power n as 2 to the power 2 square 2 to the power n, which is, if we simplify it, which will be 2 to the power 2 n. Now, what does it mean? So, we can clearly see that the number 4 to the power n has been expressed as a power of 2, which means the only prime factor of 4 to the power n is 2. And how many times we are having this prime factor 2? We are having it for 2n times. What is this? This is 2 times 2 times 2 times, like this, 2 times. How many times? How many 2 is there? 2n times. We have 2n times 2. This is what this means. So this thing is basically this. So we can clearly see that the factorization of 4 to the power n clearly contains only one prime factor, which is 2. So it doesn't have 5. But we know that for the number 4 to the power n, if it has to end with the digit 0, it must be divisible by 5, and which means that 5 should be a prime factor of 4 to the power n. But to contradiction, we are seeing that 2 is only the prime factor of 4 to the power n. This proves that 5 is not a prime factor of 4 to the power n, and this finally proves that 0 cannot be the last digit of 4 to the power n, because because 5 is not a prime factor of 4 to the power n. I hope it's clear. So definitely, if we have proved that 4 to the power n will never have the last digit as 0, because 4 to the power n will never have 5 as the prime factor. This essentially means that there exists no such n for which 4 to the power n will have last digit as 0. This 4 to the power n does not have 5 as a factor. This means 4 to the power n does not end with digit 0, and this essentially means no such n exists for which 4 to the power n ends with the digit 0. Now it says that you have already learned how to find HCF and LCM of two positive integers using the fundamental theorem of arithmetic in earlier classes. So in earlier classes, you must have already learned how to find HCF and LCM of two positive numbers using this uh, fundamental theorem of arithmetic, but maybe here you have not realized it. So uh, it says that this method of finding the HCF and LCM of two positive numbers by using the fundamental theorem of arithmetic is known as the prime factorization method. So just write it down. This point, prime factorization method. What is it? Finding the HCF and LCM of two positive integers using the fundamental theorem of arithmetic. This process of finding the HCF and LCM of two positive integers using the fundamental theorem of arithmetic is known as the prime factorization method. So it tries to demonstrate this with example 2. Example 2. It says find the HCF and HCF and LCM of 6 and 20 by prime factorization method. So it asks to find the HCF and LCM of 6 and 20 by the prime factorization method. So what it does, it first factorizes 6 like the way we discussed here. If we would like to factorize any integer we would like to factorize any composite number x and write the prime factors in ascending orders. See, if you do that for 6, we know that 6 equals 2 into 3. So 2 into 3, for 2 we know that by default the power is 1, and 20 is 2 into 10. So 2 into 2 into 5. So we have 2 into 2 into 5. This is 2 square into 5 to the power 1. Now, to find the HCF, that is the highest common factor of 6 and 2, how do we find that? HCF of 6 and 20, how do we find? From the prime factorization is obviously the answer is 2. So 2, and the LCM of 6 and 20 is is 2 into 2 into 3 into 5. Now, how are we computing? How do we know that HCF of 6 and 20 is 2 and LCM of 6 and 20 is 2 into 2 into 3 into 5? By seeing the prime factorization of 6 and 20. So here is the formula. So for finding the HCF of 6 and 20, what we do, we see the common prime factors of 6 and 20. What is the common prime factors of 6 and 20? 2, right? 2. Forget about the powers at the moment. What is the common prime factor? What is the prime factor that occurs in both the factorization of 6 and in the factorization of 20? 2 is the only common prime factor that occurs in both the 6 and the 20. So we are having 2. Now, what about the power? For the power, we see for 6, the power of 2 is 1, and for 20, the power of 2 is 2. We take the smallest power of the two powers. Over here, the power of 2, prime factor 2 for 6 is 1. For 20, the power of prime factor 2 is 2. So we will take the smallest one. That is why over here, actually it is 1. Okay. Now LCM. For LCM, what do we do? For LCM, we consider uh, uh, we consider the greatest power of each prime factor. We consider all the prime factors that occurs in both the numbers 6 and 20. Collectively, we consider we consider all the prime factors that occurs in 6 and 20, and we take the greatest power of those prime factors. Now, for 6, what are the prime factors? 2 and 6, 2 and 3. For 20, what are the prime factors? 2 and 5. So, for LCM of 6 and 20, definitely we will have the prime factors 2, 3, and 5. Now, what about their powers? What will be the power of 2? What will be the power of 3? And what will be the power of 5 in the LCM of 6 and 20? For that, for that, we consider for 2, for any prime factor, uh, we consider the highest power. So let's try to understand how LCM is working. This is the final result. Let's see. For LCM, I'm trying to explain in more details how we are finding the LCM of 6 and 20. First, what we do, we consider all the prime factors that is occurring in both 6 and 20. So for 6, we are having 2 and 3. Fine. 2 and 3. For 20, we are having 2 and 5. So we have already considered 2. Now we need to just consider 5. So 5. Now what about the powers? What will be the power of 2, what will be the power of 3, and what will be the power of 5 in the LCM of 620? How do we find the powers? So for powers, for 2 we see what is the highest power of 2 in the factorization of 6 and 20. For 6 it is 1, but for 20 it is 2. So we consider the highest power 2. So over here it will be 2. What is the highest power of 3 in the prime factorization of 6 and 20? For 6 the power of 3 is 1, and for 20 there is no power. So 1 is the highest. So 1. What about 5? What is the power of 5 in 6? There is no prime factor 5. There is no prime factor 5 in 6. So so in the the power of 5 in prime factorization of 20 is 1. So we consider 1. So in the textbook, it has given a written description how to find the HCF and LCM of two numbers uh, as you can formally write it down like this. Let's say if, HCF of A and B. Let's say we are trying to find the HCF of two positive numbers A and B. So what will be the formula in descriptive form? It says product of the smallest power of each common prime factor in A and B. So what does it say? Product of the smallest power of each common prime factors. So first we see what are the common prime factors of A and B. So we do prime factorization of A. We express A as the prime factorization. We express B in the form of prime factorization. We write the prime factors in ascending orders. Just like for 6 we did 2 into 3. For 20 we did 2 into 2 into 5. Similarly, we will do for express x, A and B, and we'll write their prime factorization. Now we will consider the common prime factor. So the prime factors which occurs in both A and B, and we will consider the smallest power of the common prime factor. Just like over here for 6 and 20, the smallest power of the prime factor 2 is 1, because over here we have 1 and over here we have 2. The smallest between 1 and 2 is 1. Now the LCM A and B, it says product of the greatest power of each prime factor of uh, of A and B. So for LCM, what is the how do we find LCM? It is the product of the greatest power of each prime factors of A and B. We write down all the prime factors that are involved in A and B, and for the powers we consider the greatest power of that prime factors that is occurring in A and B. And in the textbook, it also says that from this formula we can see that so as you can see for 6 and 20 the HCF is 2 and the LCM is 2 square into 3 into 5, and it says that if you multiply the HCF an LCM of 6 and 20, what do we get? It says we get the product of the two numbers. Yes. So it says that it the formula becomes that HCF of A and B multiplied by LCM of A and B, where A and B are two positive integers, equals A into B. This is a very important result or formula which you should remember, this one, because for 6 and 20 you can see HCF of 6 and 20 is 2 and LCM of 6 and 20 is 2 square into 3 into 5. If you multiply them, you will see it is becoming 6 and 20. The example 3, let's see the example 3. It says find HCF of 90 and 404 by prime factorization method hence find their LCM. So it says the two positive numbers are given, 90 and 404. It asks to find the HCF by prime factorization method, and also it asks then to find the LCM of 90 and 404. First, we need to write down the prime factorization of 90 and 404. So 90 is 3 into 3 into 3 into 3, 9, and then 10, 2 into 5. But we need to, it's better to arrange the prime factors in ascending orders. So we write at with 2 into 3 into 3 into 5. I hope it is right. 9, 10. Okay. And then we write the powers. We combine the same primes and have the powers. So we have 2, 1 into 3 square into 5, 1. Similarly, we write down the prime factorization of 404. 404. 404 will be 4 into 101. 101. 101 is, I think 101 is a prime factor, is a prime number itself. So it will not have any factors. So we can write it as 2 into 2 into 101. This becomes 2 square to 101. So now what will be the HCF? HCF of 90 and 404. How do you find it? So the process was, first you write down the common prime factors of 90 and 404. So what are the common prime factors? Forget about the powers. Write down the common prime factors. 90 has prime factor 2 and also 404 has prime factor 2. So so the only common prime factor is 2. Now the power. We take the smallest power. Over here the power of 2 is 1 and over here the power of 2 is 2. So we take the smallest power. So 1. HCF is HCF is, why it is 2 square? 90 What was the number? Oh, it was 96. Sorry, I have written 90. My mistake. This is 96. This is 96. 96 and 404. Okay. So we have to prime factorize 96. Whole thing is wrong. My bad. I'm sorry. So 96. 96. What is 96? 4 into uh, 4 into 24. Is it? Yes. This is 4 into 4 into 6. This is 4 into, so uh, 2 into 2 into 2 into 2. This becomes 1 4. Then 2 into 3. So 4, we have 4 into 4, we have 4 twos, 1 2 3 4, and for 6 we have 23. So we have 5 to this. So now the common prime factor is 2, and we take the smallest power. Over here we have the power of 2 is 5, and for 404 we have the power is 2. The smallest between 2 and 5 is 2. So the HCF will be 2 square equals 4. Now, now it asks what will be the LCM. We know that HCF of 90 and 404 into LCM of 90 and 404 will be equals to 90 into 404. 404. We know this formula from this, the boxed formula. Now, we know HCF is 4. So 4 into LCM 90 4 equals to 90 into 404. This means LCM of 90 404 equals, we divide this thing to the right hand side with the 4 and we get by 4, which is 90 into 101. What is the answer in the textbook? No, it is wrong. Oh, okay. So it has multiplied. It has further done the multiplication, and the answer is 9696. Okay. Now let's see example 4. Example 4, what does it say? Find the HCF and LCM of 6, 72 and 120. So we are given 3 positive numbers and we have to find the HCF and LCM using the of these 3 numbers using the prime factorization method. Find HCF and LCM of 60, 72 and 120 using prime factorization method. Okay. So let's see if I can solve this without seeing the textbook. So first we have to write down the prime factorization of the given 3 numbers. For 6, we know it is 2, 1 into 3, 1. For 72, we know it is 6 into 12 equals to 2 into 3 into 4 into 3. Now, if we arrange the prime factors in ascending order and combine the similar prime factors and have powers, we get over 4, 2. So we get 2, 3 into 3 square. Okay, so 120 is 12 into 10, which is 2 into 6 into 2 into 5. This is 2 into 2 into 3 into 2 into 5. This is 2 cube plus into 3 1 into 5 to the power 1. So we have done the prime factorization of the given three numbers. So HCF of 6, 72 and 120, what will be? First, we identify the common prime factors. In 6 we have 2, 3, also in 72 we have 2, 3, also in 120 we have 2, 3. So 2 and 3 are the common prime factors. We write it down. Now, what about the powers? The power of 2 will be the smallest power of the prime factor 2 occurring in the three numbers. What is the smallest power? Over here we have 3, over here 3, over here we have 1. So the smallest power will be 1. For 3, over here we have 1 square and 1. So 1. So the HCF is 6. What about now okay, now LCM. For LCM, we will directly apply the formula. Uh, from here, you know the formula, the boxed one, we can say that LCM of A and B equals to A into B divided by the HCF of A and B. So LCM of 6, 72 and 120 equals 6 into 72 into 120 divided by the HCF of 6, 72, 120. This is 6 into 72 into 120 divided by 6. This is 720 into HCF is 6. Okay, fine. And the LCM is so the LCM must be the product of the numbers divided by the HCF. So 6 into, why in the textbook it is 360? So HCF is 6. So 2 to the power 3, 3 square, 5, one of the greatest powers of the prime factors in the inverse numbers. So LCM is this 360. Remark, notice 6 into 72 into 120 is not equals to HCF. So the product of three numbers is not equal to the product of the HCF. Okay. So I was thinking that this boxed formula, that HCF of A and B into LCM of A and B equals A and to B, will also be applicable for three numbers. Let's say if we have three numbers A, B and C, I was thinking that we can say that HCF of A, B and C into LCM of A, B and C will be equals to A, B and C, but that is not the case. It is false. So we cannot apply this boxed formula for three numbers. So we have to go by the proper definition of LCM, which is the product of the greatest power of each prime factor of A and B. So I was proceeding in a wrong way. This is an important concept. You should remember that this boxed formula only works for two positive integers, not for more than two positive integers. Okay. So this is wrong. So For LCM, what do? We write all the prime factors that are happening, that are occurring in the prime factorization of the three given numbers. So what are they? From 6 we are getting 2 and 3. For 72, 2 and 3. So definitely 2 into 3, and for 120 we have 5. So 5. Now what about the powers? For powers of 2, we have to consider the highest power of 2 that is occurring in the prime factorization of the three numbers. So the highest power is 3. So 3, what is the highest power of 3? Is this is squared, this 3 squared. So square. And what is the highest power of 5? 1, 1. So this is the LCM. This is 8 into 9 into 5, and this is 3 60. Okay, let's try to solve the exercise problem. Exercise 1.1. Exp1, number 1, it says express each number as a product of its primes. So express each number as a product of prime. Basically, it's asking for to find the prime factorization of a number as a product of prime factors. Okay, what are the numbers? 1 is 140. So this is 14 into 10. This is 2 into 7, and this is 10 is 2 into 5. And if we now arrange the prime factors in ascending order, we get this. And if we combine the similar primes and have powers, we will get this. So this is the prime factorization. Okay, now number 2 is 156. 156. Okay, so 4. Can we? No, it is dividing by 4. No. 4 3s are 12. 3. No. Okay, let's do it step by step. 2 into 7, 88. So this is 2 into 2 into 3, 6, 9. This is 2 into 2 into 3 into 13. Now we cannot further break it down into factors because we are already having the prime factors. If we now combine the similar primes and have powers, we get 2, 3, and 13. It's always good to arrange the prime factors in ascending order, combine the similar primes, and have powers. So 3, 3, 8, 2, 5. Definitely it will be divisible by 5. So let's divide by 5. What do we get? 6. No. We divide by 5, we get 7, 35. 35, 3, then 6, and 5. So this is this. Now we again factorize 765. 5 into 5 into 1. 5 into 5 into 1, 2, 5, and 3. 15, 15, 25, 26. Yes. Now 153 is a prime number, I guess. It cannot have further prime factors. Oh no, it will. So let me check once again. 5 into 7, 35, 3, 6, 30, 225, okay. 765, if we break it down further, we have 5 into 1, 2, 25, and 3, okay. Now, this, 3 into 51. We are having this 3 into 51. 51 can again be factorized as 3 into 17, and we are done. 17 is a prime number. It cannot be factorized further. So if you now arrange the prime factors in ascending order and combine the similar primes to powers, it becomes 3 square into 5 square into 17 to the power 1. We should write 1 over here. 1. This is the prime factorization. Okay. So what else? 5005. Okay. So 5 into 1001. Can we factorize 1001 further? Is it divisible by 3? 313? No. Is it divisible by 7? 3. 20. Yes, it is divisible by 7, I guess. 5 into 7 into 1, 1, 3, 4, 28, and 3. So if you multiply 5 and 147 and 143, it is 1001. So let me check once again. 143 into 7 is 1001. So 1, 21, 28, 30. Yes. Now 143. Can we factorize it further? Divisible by 3, no. Uh, divisible by 9, 5, no. 7, no. 11, 11, no. 11, 11, 11. Yes, it is divisible by 11, I guess. So 5 into 7 into 11, we get 1 and 3. So 13 into 11 is 143, I guess. 13, 13, 143, yes. Now these cannot be further factorized because we already have got prime factors. Now if we arrange the prime factors in ascending order, it is already in ascending order. So this is the prime factorization. This 5, 7429, it is a pretty big number. Okay. 7429, is it divisible by 9? 9, 8 is 72. 2, 18, 4, 49, no. Let's try 3. 3 into 3 to the 6, 1, 3, 12, 21, 7. No, it is not also divisible by 3. 3 is 6, 3 4 is 12. No, it is not divisible by. Mm, 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 mm. Now, is it divisible by 7, 1, 06? No. 7 is 106. No. 9, 11, 11, 66, 66, 8. No, yes, 8, 82, 82, 77, 5. No. what will be the, is 7429 is a prime number? If it is so, then it will have no further prime factors. I will leave this. uh, 13, is it divisible by 13? uh, 13. Hmm, 6, no, 5, 65, 65, 9, 92, 13, 92. 7, 4, 2, 9, 5, 65, 9, 2, 7, 7, 91, 1, 9. No. In my opinion, this should be this. I'm not sure of this. I will have to check. Now, 2, question mark. I'm not sure of this. Let's do problem number 2. What it says, find the LCM and HCF of the following pairs of integers and verify that LCM and HCF equals to product of two numbers. So, find HCF and LCM and verify that HCF into LCM equals to product of the two numbers. Okay, so one is 26 and 91. Okay, so first we have to find the prime factorization of the given two numbers. 26 is 2 into 1, 3, and we are done. What about 91? 90, 91, 7 into 1, 3. Okay, so HCF 26, 91, 91 is, first we write down the common factors, which are 2 into 7 into 13. These are the common factors. Sorry, the common factors is only 13. The common factors is 13. 13, and we have only power 1. So 1, 13 is the HCF. Now LCM. LCM. If you write down all the factors, 2 into 7 into 13. And now for the powers. For powers of 2, we consider the largest power. The only factor of 2 is happening in 26, it has power 1. So similarly for 7, you have only one factor, 1, 1. And for 13, the highest power, both the power of 13 in both the numbers are 1, 1. So 1. Okay. Now it's says to verify whether whether HCF of 26 and 91 into LCM of 26 and 91 equals 26 and 91. This implies HCF is what? 13. LCM is what? 2 into 7 into 13. So 26, as we have know, if we use the prime factorization of 26, it is 2 into 13, and for 91 we know it is 7 into 13. So is this true? The left hand side is equal to right hand side. 13 into 2 into 7, 13. Yeah, this is true. True. We have verified that HCF product of HCF and LCM of 26 and 21 equals the product of 26 and 21. 91, sorry. Number 2, 510 and 92. We have to first find the prime factorization. This is 5 into 102. 5 into 102. Now, this is 5 into 2 into 51. This is 5 into 2 into 3 into 17. So this becomes 2 1, 3 to the power 1, 5 to the power 1, and 17 to the power 1. Okay, now let's prime factorize 92. Uh, yes, 4 into 23. 23 is a prime factor, so 2 into 2 into 23. This is 2 square into 23. Hmm. Hmm. How many problems are there? Okay. So HCF of 510 and 92. How do we find that? We first write down the common prime factors. What are the common prime factors? Only 2 and 2. What is the smallest power of 2? 1. So 1, this is the LCF, HCF. And LCM, we write all the prime factors, all the prime factors. Over here, we have 2 into 3 into 5 into 17, and for 92 we have the 23. Now we consider the highest power for all these prime factors that are occurring in the prime factorization of the two numbers. For 2, the highest power is 2. For 3, the highest power is 1. For 5, the highest power is 1. For 17, the highest power is 1. For 23, the highest power is 1. So this is the LCM. Now it asks to verify whether HCF into LCM, HCF into LCM, what is this? Whether it asks to verify whether this equals 510 into 922 or not. This implies, what do we have? HCF 2. What do we have? LCM 2 square into 3 into 5 into 17 into 23. And if we substitute 510 and 92 by the prime factorization, we get 2 into 3 into 5 into 17 and into 2 square into 23. Now check if the left hand side is equal to the right hand side. 2 we have 2 cube on the left hand side. Right hand side we also have 2 cube. 3, 5, 7, 23, 3, 5, 7. Yeah, this is true. True. Number 3. 3, 3, 6 and 54. Let's do prime factorization of 336, which becomes 3 into 112. This is 3 into, is it divisible by 312? 3 3 is a 9. No, definitely by 2. So 2 into 556. Okay, so 2 into 56. We can further factorize 56 as 4 into 14. 4 into 14. This becomes 3 into 2 into 4 into 2 into 7. If we now if we arrange the prime factors in ascending order and combine the similar primes, we get 2, 2, and over here 4. So we have 4 2's. So 2 to the power 4 into 3 to the power 1 into 7 to the power 1. Now 54 is 2 into 2, 7 equals 2 into, we know that 27 is this. So 2, 1 into 3 cube. So what is HCF? HCF 3, 3, 6, 54. We first write down the common factor. The common factors are 2 and 3. Now, about the powers, we write, we have the smallest power. The smallest power is 1. So, between 4 and 1, 1 is the smallest power. So, 1. For 3, it is also 1. Now, LCM. We first write all the prime factors. That is 2 into 3 into 7. These are all the prime factors that are occurring in the occurring in the prime factorization of the two numbers. Now, what about the powers? For power of 2, we consider the greatest power. The greatest power is 4. What is the greatest power of 3? It will be 1. And for 7, it is 1. Now, uh, it is asking to check whether 336 HCF into LCM is equal to 336 into 54 or not. This implies HCF we got 2 into 3 and LCM we got 2 to the power 4 into 3 into 7. Okay. This, if we substitute the 336 and 54 by their prime factorization, we get 2 to the power 4 into 3 into 7 into 2 into 3 cube. So, and we need to check whether the left hand side is equal to the right hand side or not. In the left hand side, we have 2 to the power 5. Also, in the right hand side, we have 2 to the power 5. In the left hand side, we have 3 square. But on the right hand side, we have 3 to the power 4. So, something wrong we must have done. In the LCM of 336 and 54, the power of 3 will be 3 because the highest power is 3. This is wrong. This should be 3. And this should be 3 and now it is correct. So, it's 2. Okay. Now, problem number 3. It is asking to find LCM and HCF of the three numbers by applying the prime factorization method. Okay. Find HCF and its LCM by prime factorization method. So 1, the given numbers are 12, 15, 21. Let's do the prime factorization. 2 into 6 equals 2 into 2 into 3. This is 2 square into 3 to the power 1. 15 is 3 1 into 5 1. 21 is 3 1 into 7 1. So the HCF of 12, 15 and 21 will be, first we write down the common prime factors. The common prime factors. So the only common prime factor is 3 and the power will be the smallest power, it is 1. So the LCM of 20, 15 and 21, first we write down all the prime factors, which will be 2 into 3 into 5 into 7. Now the powers of 2 will be the smallest powers of 2. The only power of 2 we have is 2, so it will be 2. For 3 the smallest power is 1, for 5 it is 1, for 7 it is 1. So okay, let's do what is 2, 17, 23 and 29. 17 is a prime number itself, so the only prime factorization will be 17. 23 is also a prime number, so the prime factorization will be 23. 29 is also a prime number, so the prime factorization will be 29. So HCF of 17, 23, 29, we write down the common. Now we don't have any common prime factor, so if there is no common prime factor between two positive integers a and b, the HCF is 1. No common prime factors, so the HCF will be 1. LCM LCM is, we first write down all the prime factors, which is 17, 23 and 29, and we, for the powers, we consider the smallest powers, and the only, so definitely the smallest powers will be 1, 1 and 1. Number 3, 8, 9, 25. This will be same as 2 because 8 is 2 into 2 into 2, that is 2 cubed. 9 is 3 into 3, that is 3 square. 25 is 5 into 5, that is 5 square. So HCF of 8, 9 and 25, we first have to write the common factors, and there is no common factors, so HCF is 1. And LCM, we write down first all the prime factors, which are 2, 3 and 5, and for the powers we consider the highest powers. So quite obviously this will be 3, this will be 2 and this will be 2. Okay. Now problem number 4, what it says, given HCF 3 HCF 306, it is given that the HCF of 307 and 3 and 657 is 9, then find the LCM. So definitely we have to first, okay, so given HCF is of two numbers is 9 and find LCM, so it is dealing with two positive numbers, and we know from the formula this will hold true. We know this from the formula that the multiplication product of HCF and LCM of two numbers is equal to the product of the two numbers. So this implies HCF is given as 9 and LCM equals 306 into 657. This implies we get the LCM 657 as 306 into 657 divided by 9. So you have to simplify this value and get the answer. I'm not doing that. Okay. So problem number 5. What is problem number 5? Check whether 6 to the power n end with digit 0 for any natural number n. So in the example, it is similar to the example in the solved example we did earlier, where we were trying to see if the number 4 to the power n ends with the digit 0. Similarly, we will proceed here, and so 6, the basic concept we are applying is that 6 to the power n, we are doing a prime factorization of 6. We are applying the prime factorization of 6. That is the core concept to solve this problem. So solution 6 to the power n, we can prime factorize 6 as 2 into 3, and then we have n. This means this is 2 to the power n into 3 to the power n. Now, okay, it says that 0, the 6 to the power n, is there any natural number n so that 6 to the power n will have 0 in the as the last digit. So for 6 to the power to have 0 as last digit implies 6 to the power n must be divisible by 10. This also implies 6 to the power n must be divisible by 5. This means 5 must be a factor of 6 to the power n. But this thing we have already done the prime factorization of 6. 6 to the power n, we know that it is 2 to the power n and 3 to the power n. We don't have any prime fact, we don't have any factor of 5. Do not have the factor 5. But 2 to the power n has no 5 as factor. This so since this implies 2 to the power n or is not so to have 6 to the power n, to have the last digit as 0, definitely it must be divisible by 10 for sure. 6 to the power n must be divisible by 10, only then it will have a 0 as the last digit. Now so 6 to the power n should be divisible by 2 to the power, should be divisible by 10. So 10 we can write it as 2 into 5. That means 6 to the power n should definitely be divisible by 5. But we are seeing that 2 to the power n into 3 to the power n has no 5 as factor. So definitely this implies that is not divisible by 10. This implies this number does not have 0 as last digit, hence proved. Okay. 6. Problem number 6. What does it say? Explain why are composite numbers. Okay. Explain why 7 into 11 into 13 plus 13 is a composite number. Now, when it says that explain a given number is a composite number, it is essentially trying to ask that can we write the given number as product of prime factors. So the given number 7 into 11 into 13 plus 13. So from here, if you take 13 common, we'll get 7 into 11 plus 1. This is 13 into 77 into 77 plus 1, 78. This is 13 into 2 into 6, 39. This is 13 into 2 into 3 into 13. This is 2 into 3 into 13 square. So the given number has been prime factorized. We can see that the given number has a factor of primes 2, 3 and 13. So any composite number, we know that any composite number can be written as a product of prime factors. So we have expressed the given number as a product of prime factors. This is product of prime factors. This implies this implies 7 into 11 into 13 plus is a composite number, as every composite number as every composite number can be expressed as a product of primes. This was part 1. Part 2 is we have to prove that the number 7 into 6 into 5, 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 is a composite number. Okay. So 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5, if we take 5 common, we get 7 into 6 into 4 into 3 into 2 into 1 plus 1. And okay, so this is let's say this part is let's say whatever this part is, let's say this part is n. So we get 5 into n. Now, definitely 5 into n, whatever the value of n is, it is some natural number. 5 into n is always a composite number because it has at least one prime number as a factor, because a number which is not a composite has to be a prime number, and a prime number has no factors other than the number itself and number 1. So this implies 5 is a factor of given number. This implies given number is a composite number as every composite number every composite number has at least 1 prime as a factor. I hope it's clear. 7. What does the problem 7 says? There is a circular path around a sports field. Okay. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time go in the same direction. After how many minutes will they meet again at the starting point? There is a sports field, circular sports field. Sonia takes 18 minutes to drive one round of the field. 18 minutes, Sonia. So let's say Sonia and Ravi starts from this point. Uh, for Sonia, let's say uh, it completes the circular field and comes to the same point in how many? What is this? Okay. Sonia uh, takes 18 minutes to drive one round of the field. No, it's bad drawing. Hmm. Hmm. So for Sonia to complete one circular round and come to the same point takes 18 minutes. For Ravi, uh, for Ravi, let's say hmm, to complete the same uh, field once is 12 minutes. 12 minutes. So the question is after, if they start from the same point and go in the same direction, after how many minutes they will meet again. So basically this is a problem based on the HCF and LCM. So the concept is after, as you can see, after in 12 minutes Ravi has already covered one round. Mm, and Sonia will take 18 minutes to cover the one round. Mm, 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 mm. Then after how many minutes will they meet again at the same? Uh, After how many minutes they will meet again at the starting point? Okay, so it's asking after how many minutes will they meet at the starting point? Okay, so let's assume let's say after n minutes they both meet at starting point. I can sense that the answer will be the LCM of 18 and 12. So let's try to understand why the answer will be LCM of 18 and 12. So the LCM of 18 and 12 is uh, 18. If we do prime factorization, is 2 into 3 square, and 12 is 2 into 2 into 6. So uh, 2 square into 3 1. So LCM LCM of 18 and 12 will be uh, will be 2 square into 3 square, which is 4 into 9, 36. Now let's try to understand why the answer will be 36 minutes. So for Sonia, it takes 18 minutes to cover one round. So in 36 minutes, it will cover two rounds. And in 36 minutes, Ravi will cover three rounds, and then they both will be at the same starting point. Hmm. The question is, uh, after how many minutes will they meet again at the starting point? The question, I mean, the question should have been, what is the earliest minutes? What is the earliest time that they will meet again at the starting point? What is the minimum number of minutes after which they will again meet at the starting point? In that, so the answer will be the LCM of 18 and 20, because in after 18 minutes, Sonia reaches the starting point again, and by that time Ravi has already reached the starting point and also have gone a little farther away. Uh, so the answer is 36 definitely, but how do we logically, how do we provide the reason why the answer is the LCM of 18 and 12? So when do they meet? After how many minutes they again meet? If I assume, let's say after n minutes, they both meet at the starting point. From this, what we can have? So in n minutes, uh, mm, in n minutes, how many rounds Sonia has taken? It will be n by 18. And how many rounds Ravi has taken? It will be n by 12. So mm, 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 so will the number of rounds taken by Sonia and Ravi after n minutes will be the same? No, it will not be same. But mm, okay, I'm not able to give a proper reasoning, but why the answer will be LCM of 18 and 12. If you can convince yourself that uh, the answer will be LCM of 18 and 12, it is good. And if you can if you can conceptually understand the reason why the answer will be LCM of 18 and 12, you can share uh, your understanding in the comment section. So we have completed exercise 1.1, even though I couldn't properly solve the problem number 7. Sorry for that. So with this, the lecture 1 comes to an end, and I hope uh, this video will help you in understanding whatever we have discussed until the section 1.2. So we have discussed, let's quickly revise what we have learned. Uh, we have learned the Euclid's, we have learned about Euclid's division algorithm and fundamental theorem of arithmetic. We have applied, we have learned how to do prime factorization of any natural number, and we have uh, learned the fundamental theorem of arithmetic, and using this theorem we have find the HCF and LCM of two given positive integers, and also we have find the HCF and LCM of more than two positive integers. That is, fundamental theorem of arithmetic can be used to find HCF and LCM of multiple positive integers. And also we have understood, we have discussed the solved examples, and we did exercise 1.1 even though I couldn't properly solve problem number 7. Thanks for watching, and please stay tuned for the next lectures, and also eventually all the future lectures, as I will be sequentially discussing all the chapters as it is given in the NCERT textbook. And once a chapter is finished, I will solve the exemplar problems from this chapter. So that will be very important. Please do not miss that video where I will be solving the NCERT exemplar problems. Solving the NCERT exemplar problems is a must to have to test your understanding and skills on the chapter concept, and also for your board examination. Thanks for watching, and until the next video, take care and bye.